Alright, now I want to talk about something called the squeeze theorem. This was initially covered in lesson 2.1. I did not have a chance to go over it in lesson 2.1. So here's the theorem itself, and then with an example or two, I'll explain what this theorem is used for. Okay, if you have three functions, let's say g of x, f of x, and h of x, and if the function g of x happens to be less than or equal to f of x, and the function f of x happens to be less than or equal to h of x, for all values of x, okay, for all values of x that's not equal to c, some other c, in some interval about c, some interval that contains c, and if the limit of g of x happens to equal the limit of h of x when x is approaching that c value, and that limit happens to be L, then function f of x has no choice. The limit of the function f of x as the x is approaching c has to be in between those values. So in turn, that value also has to be L as well. In the case, the squeeze theorem is also known as the sandwich theorem. I don't know why I need to say that, but okay. But you get the idea. Okay, it's the limit for f of x is being sandwiched or being squeezed in between the limits of g of x and h of x. So before getting to the book's example 9 from lesson 2.1, I'll give you an example that's easier to, what at least to me, it's easier to understand and explain. But it's not as practical because you don't have to use the squeeze theorem to get the limit value for this one. You could, in fact, you could just use a direct substitution method to find the limit because your function, your expression is defined, okay, with this x value. At 0, it is defined, so you could use 0 as your substitution value, and then you could figure out the limit. But let's use the squeeze theorem. Let's see what the squeeze theorem deal is, okay? So to use the squeeze theorem, usually we start with sine or cosine because these are the values of sine and cosine will oscillate in between -1 to +1 and anything in between that. Okay, so this is what we know. So we know that -1 is less than or equal to sine of x, and sine of x is less than or equal to +1. But we're concerned with finding the limit for the product of x and sine of x. So what I do is, on the next step, I can multiply the sine of x by x by multiplying both sides of the inequalities, the compound inequality, by x as well. You're allowed to multiply to both sides of an inequality by the same quantity. So we got that so far. And then if this is true, then the limits of -x, and then we'll choose the c value to be 0 as if x approaches 0, must be less than the limit of x times sine of x as x is approaching 0, which is less than or equal to the limit of x as the x value is approaching 0. Okay, but we know that the limit of -x as x gets close to 0 is 0, and the limit of x as x gets close to x approaches 0 is also 0. Okay, so now take a look at this. So the limit of x approaching 0 of x times sine of x must be in between 0 and 0. So by the squeeze theorem, okay, we've demonstrated enough conditions for us to use the squeeze theorem. So by the squeeze theorem, we can conclude that the limit of x times the sine of x as x approaching 0 is indeed 0 as well, because it's in between 0 and 0. So that's a simple example, simple application of what a squeeze theorem is. Graphically speaking, take a look at this. Okay, I graphed y equals x, I graphed y equals -x, and I graphed the graph of x times sine of x. And you can see it's clear to you that the function, the green function, the graph of x times sine of x is in between. It's sandwiched in between for all x values between -x and x. And you could also see that as the x value is getting close to 0 from either side, your y value, it's also getting closer and closer to 0. So the limit of the function x times sine of x is 0 from the other side. So that's the limit itself. Okay. So now to set you up for example 9 from lesson 2.1, you use the same idea. You do have to know the fact that sine of 1 over x is also in between 1 and negative 1. You can check with decimals if you're not sure about that. Okay? And then we're just multiplying both sides by x squared. So you get negative x squared is less than or equal to x squared times sine of 1 over x is less than or equal to positive x squared. But if you were to take the limit of each as x approaching 0, then you will get 0 for every parts of that compound inequality. 0 for this, 0 for this, and 0 for this. And then you could conclude that the limit is 0 by the squeeze theorem.